we were talking about the characterization of light and wavelength and color and all of that, and we learned about the spectrum of visible light. When atoms or molecules absorb energy, that energy is often released as light energy. An example of this are fireworks and neon lights. So this is a neon light, and that orange glow is characteristic of the element neon. That actually has neon gas in a tube and an electrical voltage being applied across it. The electrical energy causes the neon atoms to absorb energy, and then they release that energy as visible light with that color. Beautiful fireworks you may see on the 4th of July. The different colors here are different elements. They've accepted energy, absorbed energy from the explosion, and then they're releasing it as light. This is a lamp, kind of like a neon lamp, except not advertising anything. This lamp is filled with mercury. This one has helium in it, and this one has hydrogen in it. And we'll actually get to look at some lamps like that when we do the experiment for Chapter 8. When the light is passed through a prism, light from one of these elements, instead of seeing a continuous spectrum, a rainbow, we see a pattern of particular wavelengths of light. It's called an emission spectrum. And so we'll see some colored lines and then darkness in between. This can be used to identify an element, much like a fingerprint or a barcode. It's unique to that element. And classical physics cannot explain why this happens. So here's the setup. There's a lamp, and here's the hydrogen lamp, and the light that's emitted from the hydrogen molecules comes through here, goes through a slit, and instead of seeing a rainbow, we see the 3 distinct lines, well 4 if you count that little guy over there. We would expect to see a rainbow of light, but we only see a few lines. And in between, there's darkness. So the light being emitted only has a few wavelengths of light in it, and those get separated, and we can see which ones they are. And this is why they are different colors, is because if they had all the colors, they would appear white. So the helium spectrum has more lines in it. This is barium. Here's oxygen and neon. And these two are showing a lot of background noise. This color green here is not coming from the oxygen itself, just the brighter lines. Does anybody have any questions about that? You know, you can play with little pieces of glass and stuff and sometimes get a rainbow to form from sunlight, right? Or even if the sprinklers are going off, you can sometimes get in just the right position and see a rainbow. And it's always a continuous spectrum because it's the light from the sun. If it was just hydrogen light, we would see 3 or 4 lines with nothing in between. That would be interesting. Yeah.
You said classical physics doesn't have an answer to that?
Correct.
Does quantum physics have an answer to it?
Quantum physics has an answer.
Okay.
Yep. Yeah. So we can also get elements to absorb light. So for mercury, if we're exciting it, say with electricity, we can get light that's emitted from it. We can also pass light through it and see what wavelengths get absorbed. So here these are getting absorbed, and so we see dark lines where there's no light is exactly the opposite of the emission spectrum. Elements can be identified with flame tests. Here you can take something like sodium chloride on a little wire here and stick it into a flame, and you'll get a particular color for sodium. This is a very common color for fire, right? I mean, you always think of fire as kind of warm, yellowy orange, bright color, right? That's because there's sodium everywhere, right? So that will often contaminate the colors that you observe from other elements. Potassium gives this little lavender, lithium's bright red, and barium has this greenish tint to it. If there's any sodium present in this barium solution, the brightness of the sodium emission is going to completely overpower the barium and you won't see it at all. And we'll have a chance to look at that as well in experiment 8. So they observed this phenomenon and didn't know what was going on, but a guy named Johannes Rydberg found that he could describe those spectra using an equation. And the equation had 2 integers in it, and this is his equation. 1 over the wavelength is equal to a constant times 1 over m squared minus 1 over n squared. And n and m were integers. And those would describe where the lines were. So that's, nice and everything. But it doesn't explain why elements do this, why they give off discrete lines. It doesn't explain why atoms are stable. He didn't even understand why his equation worked. It just did. Kind of wonder, how many equations did he try before he came up with this one? So let's review Rutherford's nuclear model of the atom. The atom has a tiny dense center called the nucleus. That's where the protons and neutrons are. Almost all the mass of the atom is in there, and that nucleus is positive charge on it. The rest of the space in the atom is occupied by really tiny electrons. They're just moving around in empty space, and they have negative charges, right? And so far we have not talked about what are those electrons doing in that empty space. So the problem here is electrons are moving charged particles. And according to physics, if you have a moving charged particle, it's going to give off energy. So then we might expect atoms to glow because they're giving off energy. They will glow when they are excited by, say, electricity. Then they should just be glowing all the time, but they're not. The bigger problem is that these electrons should be losing energy and then crash into the nucleus, and the atom should collapse. Because these electrons are attracted to the positive nucleus. And what keeps them away from it is their motion, right? So you think about a satellite in orbit around the Earth, right? It needs to have the correct speed and be the correct distance from the Earth to be in a stable orbit. If it gets too close, it's going to get sucked in by gravity and it will crash. But these electrons just keep going and going and going. So this model doesn't explain either what's happening when we gain or lose energy in the atom, or why we get these discrete lines. So Niels Bohr, who was the one he said he really didn't like quantum mechanics, and that it, it's just disturbing, basically. He developed a model of the atom that helped to explain what's going on with these energy transitions. And I'll just tell you right now, it turns out his model is wrong. But we still use it because it's a helpful step into thinking about the quantum mechanical model. So Bohr's model of the atom resembles the solar system. So we have electrons traveling around the nucleus in circular orbits, like planets orbiting the sun. Those orbits exist only at specific fixed distances from the nucleus. That's also true of our solar system. And the energy of each orbit is fixed. We say that's quantized. There are only certain energy platforms possible. The amount of energy in the atom is then related to the electron's position in the atom. So let's just talk about what quantized means for a minute. So this is a ladder. And it has rungs, right? You climb up a ladder to get higher. Well, you can stand on the first rung, or the second rung, or the third rung. Can you stand halfway between two rungs? No, you can't. It's not one of the options. Our monetary system, coins and bills, is quantized. There's a penny and a nickel and a dime, 25 cents, 50 cents, $1. And you get into the bills, there's 5, there's some 2s out there, 10, 20, 50, 100. There's no $75 bill. There's no 3.5-cent coin, right? Why? There aren't. It's quantized. There are only specific levels possible. The opposite, sort of quantized would be continuous. So if instead of going up a ladder, you went up the side of a hill, well, you could be the same elevation as the first rung on that ladder or the third rung, but you could also go in between. Any elevation on the hill is possible, where here only ones corresponding to the rungs are possible. So this is what those orbits are like for the electrons in Bohr's model. You can be in the first orbit or the second orbit. You can't be in between. Any questions about that? There are lots of examples of quantized and continuous things. If you think about musical instruments, a piano has keys, right? And you can press C or C sharp, but you can't make the sound in between. What about a violin? A violin's continuous. You can make C and C sharp, but you can also make sounds in between, which I think is part of why a violin, when played badly, sounds so awful, right? Yeah. Not that piano can't be horrible too, but.
It's a slight easier.
Yeah, at least those are actual notes, right? Where on a violin you can play things that are between notes, which I guess if you're into experimental music or something, that'd be cool. Well, you could have your piano out of tune, but on the guitar, on the violin, just moving your finger a little bit, it's going to change the note. So here's an illustration of the Bohr model. So here we have the nucleus, and this is our first orbit, and second, and third, fourth, fifth. And so an electron can be in any of these orbits. We'll say that an electron received energy and got excited, and it went up to the n=5 level. It's not going to stay up there. Eventually it's going to come back down. And when it comes back down, the amount of energy that's released is equal to the difference between the energy of level 2 and level 5. The transition from 4 to 2, we can look at the wavelength of that light and calculate the energy of the light, and that energy corresponds to the energy difference between those two levels. And same for the 3 to 2. So the distance between these will determine the energy and thus the wavelength of light that's emitted. That also determines the energy of light that's absorbed. So if we looked at an absorption spectrum, we'd see a black line because the energy here going from 2 to 5 can be taken in by the atom by bumping an electron up to a higher level. And so that violet light will be absorbed, whereas the light around it will not, because that's one of the quantized amounts of energy that's possible. So the electron can be in these different states, these different levels, but it cannot be in between them. Because if it was in between them, even briefly, it would have a different amount of energy. And therefore, we should be able to detect that, at least very faintly. So it's never observed between states, it's only in one state or another, and this is called a quantum leap. Going from one state or form of being to another state or form of being without passing through space in between. Yeah?
When you talked about limiting quantize, is that like the same thing, like when you talk about discrete things, and like in mathematics, where it can be like it's counted, like where you have individual like.
Yeah, quantized is related to discrete.
Okay.
They're not exactly the same,
Okay.
but they are related.
Okay.
Yeah. So here you could say the energy levels are discrete, right?
Okay.
Because only particular ones are possible.
Okay.
Yeah. So we call that a quantum leap. And I don't know if you've watched the TV show Quantum Leap. It's a pretty cool show.
Got that.
Yeah, and so there was the old show, and now there's a new one out that's also very good. So when we look at that photon of light that gets emitted, its energy is equal to the energy difference between the two states. And then we can calculate those energies, like I said. So the Bohr model has great historical importance. It also has conceptual importance. But unfortunately, it only works for hydrogen. So that's great for hydrogen, but there's an awful lot of other elements out there, and it doesn't work for those. So it was replaced by the quantum mechanical model.